Next topic is telescopes. What is a telescope? A telescope is an optical instrument through which you gaze stars, moon, planets. That's the basic purpose of a telescope. And there are various types. We'll discuss all of them. Let's see the basic construction of an astronomical telescope. Let's look at this construction. The telescope has two lenses. One lens is this one is this one. The rays from infinity from the objects hits this lens, and this lens is called objective. The parallel rays from infinity obviously will focus at the focal point of this particular lens at a distance FO. Then this real image is taken as object for this lens through which we are seeing. Since we are seeing through this lens, this particular lens is called eyepiece. Now, if the position of this image is such that it falls exactly at focal point of this lens, like this one, then the image formed will be at infinity. Right? The second case could be that we don't put this image exactly at the focal point, but slightly away. How's that? It's like this. Again, we have the two lenses, same lenses. The image from infinity, after going through this lens, are focused on the focal point of this objective at FO. And this FO is within the focal point of this eyepiece. The focal point of this eyepiece is here, but we are slightly inside it, so that the image, these rays will not be parallel, the image will not be formed at infinity, but much before that. And it is formed at this place. The image is as compared to this erect, and it is virtual. Now let's define some points. This point where the parallel rays meet is obviously the focal point of the objective. This is the focal point of this eyepiece, and let these parallel rays make an angle theta, angle alpha with the axis, and let the image, this image, make angle beta with the axis. This point is P dash, this point is P double dash, and the image is P dash Q dash. The first image and the second image is formed at P double dash Q double dash, right? So this is the case when the rays don't become parallel, and this image is formed at normal vision at near point. So it is called least distance of clear vision. Now let's see the treatment of this. First, let's define alpha. Alpha is the angle. Alpha is this angle. This angle is defined as, can be defined as tan alpha. Since the angles are very small, this is equal to this alpha is equal to this length, P dash Q dash, divided by this length. This length is nothing but FO. Okay. Similarly, what is beta? Beta is this angle. This angle will be this divided by this distance. And beta will be defined as P dash Q dash over EP dash. This is EP dash. And what is beta by alpha? Beta by alpha will become P dash Q dash over EP dash into divided by alpha. Alpha is P dash Q dash over FO. So this gets cancelled, and what will be left is this is the expression without any adjustment. So since beta and alpha is the angular, what is beta divided by alpha is the angular magnification. So we can write magnification as FO by EP dash. Now this EP dash, if we make it equal to FE, meaning thereby if this point shifts to this point, then what will happen? These two rays will become parallel and the image will be formed at infinity. So when this condition happens, EP dash gets replaced by this thing, and this is for the condition of for normal adjustment. That means image is formed at infinity. Okay. Now let's take the lens formula for eyepiece. Let's apply our sign convention. U for eyepiece, U is here, which is against the rays, direction of rays. So is U, F will be positive. So what we get is right. Now put some values. 1 over V. For eyepiece, what is V? V is this distance. E P double dash. What is U? For eyepiece, U is this much distance. which is E P dash. This is P dash, this is E. So it is E P dash. And what is the focal length of eyepiece? Fe. Now, this EP dash, which was this EP dash, where the image is formed. If the image is formed at near point, then we can rewrite this equation as minus D minus 1 over this should be minus because, sorry, this is okay. This plus this has 1 over D, 1 over EP dash is equal to 1 over Fe. So 1 over EP dash over D now if we take our magnification formula, this one, this is without any adjustment, and here this is if we do this adjustment, so what we get is FO by FE 1 plus FE by D. This is the case of this is for near adjustment. Let's try to calculate tube length of a telescope. Tube length will be basically this length, which is FO, plus this length, which is, or rather it is OP dash plus P dash E. What is OP dash? OP dash is our focal length of objective. Focal length of objective plus P dash E. And what is P dash E? P dash E is this. This is very close to our, now if this FO or this point P is made to coincide with this focal point, then the rays will become parallel. So this will be the case of normal adjustment. So for normal adjustment, our P dash E will be nothing but focal length of eyepiece. This is when the rays are, image is formed at infinity, or this is for normal adjustment. Image is formed at infinity. Now the second case will be what? L is same as this. Now P dash E P dash E, we have already seen P dash E as this. Yeah. So we substitute this P dash here. What we get is capital D. Or this is for this one near point adjustment. Another type of telescope is called terrestrial telescope. Terrestrial telescope is exactly same as astronomical telescope, but in case of astronomical telescope, the image was virtual and inverted. So whatever you will see it inverted. Now, in order to remove this problem, what we do is we make a terrestrial telescope in which the image is still virtual, but it is erect. Now let's see the construction of a terrestrial telescope. Here, if we forget about this lens, the construction is exactly same as astronomical telescope. What we do here is we introduce another lens here, which helps in converting the direction of the image. So you have object here, the parallel rays coming from distance. This is the objective lens. Obviously, the rays are going to focus at focal point of this. Then there is another lens which converts this inverted image to this image. This is real, this is also real. Now this second image now is used as an object for eyepiece. And if you see that in this case, if we keep this point P double dash within the focal length of this lens, the image formed will be erect but muscular. Yeah. So again, this is alpha. This is P dash Q dash is the image, first image that is formed. P dash double Q dash is this image inverted, and final image is Q triple dash P triple dash. Okay. Now if we take some distances, rays coming parallel are focused on a focal point. So this distance, which is this, is focal length of objective. We place this object at 2f so that the image is also formed at 2f. So this distance and this distance will be same as 2f each. Then this distance is u for this particular lens. So this is ue. And since the image is formed here, so this distance from here to here is nothing but v of eyepiece. So here our magnification is defined as normal adjustment and this is for normal adjustment. And is also equal to FO by FE for near point adjustment. Now, if you notice, both of them are same as astronomical telescope. Now, if we calculate the tube length will be what? The distance from this lens to this lens, from here to here, is the total tube length, which comprises of addition of all these terms, FO, 2F, 2F, and VE. FO plus 2F plus 2F plus UE. This is equal to FO plus 2F plus UE. This is for normal adjustment, because this UE in case of normal adjustment will be what? This is our UE. And if this UE becomes equal to the focal length of this eyepiece, then the rays will become parallel and image will be formed at infinity for a normal adjustment. So we can replace this by instead of UE, we can take FE as the focal length as UE. So this is for normal adjustment. Now, if we use our lens formula for eyepiece, now as far as V is concerned, it is formed on this side of the lens, which is opposite to the direction of image in direction of rays. So this will become negative. So is U. U is also on the same side. F is positive. So what we get is these are all UV. Now, if this image is formed at near point, this will become or we can write U is equal to this is the value of FE, UE. Now, if we substitute this UE in this equation, what will happen? This actually is not, this is unadjusted. And it becomes normally adjusted only if we substitute UE with FE. So our unadjusted value is plus UE. Sorry, this will be F4 4. What we will get is or is equal to we substitute UE from here. This is for near point adjustment. Another type of telescope is Galilean Telescope. Now, how does it differ from other telescopes? Let's see the construction of Galilean Telescope first. In Galilean Telescope, you have the same eyepiece as in previous telescopes. You see here, the second lens is replaced by a concave lens. And now the beauty of this concave lens is that with this, without adding any extra lens, we get an erect image. Our image is erect. This is the advantage. And we don't have to use any in-between lens. So let's explore this one. This is our objective. This is our eyepiece through which we see. This is the size, PQ is the size of the object. The parallel image comes from infinity. And obviously they're going to focus on the focal point of this particular lens, which is this one. P dash Q dash is the focal point of objective lens. And this P dash Q dash is kept very close to the focal point of this, so as to get us a virtual image. So the angle that the rays, parallel rays coming from infinity makes with the axis is alpha, and the image makes alpha beta with the axis. Now, this distance, since the first image is formed at focus, this distance is focal length of objective. And the final image is formed here. So this distance is VE. V for this particular eyepiece. And for this eyepiece, what is the U? U is this distance. EP dash is UE, this one. Let's see some treatment now. But treatment is pretty much same as we have seen before. Alpha is nearly equal to tan alpha is equal to P dash Q dash over OP dash is equal to this is for tan alpha is what? P dash Q dash. P dash and Q dash over OP dash. P dash Q dash is the size of the image, first image that is formed, and OP dash is the distance from the center of objective lens. This is OP dash, which is same as OP dash is exactly same as focal length of the objective. Similarly, beta is nearly equal to tan beta is equal to this is our beta, this is also beta, opposite angles. This is equal to size of the image P dash Q dash divided by EP dash. EP dash is nothing but UE. So we can write magnification as beta by alpha This is the magnification without any adjustment. Now, if we replace EP dash, if we make it exactly as the focal point of this, then what happens? These rays will become parallel and we will get the image at infinity. So M is equal to FO by FE, which will means image is at infinity, and we call this as normal adjustment. Now again, we take the lens formula for objective for eyepiece. In this case, image is formed here, which is along the same direction as the rays of for this particular lens. So this becomes positive. U is on the other side, so it is negative. FE, this is a concave lens. For concave lens, focal length is negative. So what we get here is U is, what is U? Actually, this is UE. U is nothing but this distance, which is E P dash. Or what we get is with this V, we take it as near point. Then this is our formula. This is for near point adjustment. Now let's substitute this in our original formula, this one. This is the original formula, which was without any adjustment. So M is equal to FO by EP dash, and we substitute EP dash from here. This is equal to FO divided by and since this was minus, this becomes minus. And we rewritten as divided by D. This is for near point adjustment. Now, if you want to find out the length of the telescope, what will be the length of the telescope? The length of the telescope will be distance between objective and eyepiece. Yeah, which will be OP dash, this distance, minus this distance, which is EP dash. So length is equal to OP dash minus EP dash. OP dash, what is OP dash? OP dash is the focal length of this objective minus EP dash. This is the formula without any adjustment. And we will find our two cases for near adjustment and for normal adjustment. For normal adjustment, our EP dash should become exactly equal to the focal length of eyepiece. This P dash E or EP dash, whatever you call it, this one becomes is exactly focal length of this concave lens, so that the image will be formed at infinity. So what we get is length is FO minus FE. We take a modulus of this because FE actually will be negative. So geometrically, the distance is focal length of objective minus the focal length of eyepiece. But without taking sign convention, we make it mod, so that even if we take sign convention, the geometrical distance remain this minus this. Now, similarly for near point, we can define our L as we take it into absolute value because FE is actually negative. This is for near point adjustment. Mind it here, sign convention has to be used. Now, if we take a microscope or a telescope, is it possible that it will resolve any 2 points which may be lying close to each other. What it means is, let's say this is our object 1. This is our object 2. And this is the distance between them. If the distance is sufficient, we may be able to see clearly distinguish object 1 from object 2. But if we keep decreasing the distance, we may still be able to see further. Maybe at this place, we cannot distinguish object 1 from object 2. This is called resolution. And let us see their treatment in our optical instruments. Let us take the case of a microscope. In microscope, this is our objective lens. The object is put in front of the objective. Let us say there is one object O1, this one. There is another object O2, this one. And we put our eye here to see the image of this. We've seen it earlier that because of diffraction, the intensity of these images will vary. And if we plot it, this is the red one, this is the blue one. And if the blue one, the maxima of the blue one falls on the first minima of the previous one, then we are just able to resolve it. Meaning thereby, if the distance between maxima of this and maxima of this, which happens to be coinciding with the first minima of this, let's call this distance as B. This is the minimum distance that can be resolved. Okay. So let us say this is wrong. Okay. This is the DM, distance between two objects, O1 and O2, close to each other. A is the aperture of the convex lens. F is the focal length of this convex lens. And we view our image of these 2 points here at a distance V from the lens. Okay. Then according to Rayleigh's principle, we cannot resolve any angle subtended less than theta, which is given as where lambda is the wavelength of light used, and this is the aperture through which both these objects are going to be seen. In our case, so A is the aperture, which in our case is the full diameter of the lens. This distance B, which is the minimum distance required for the 2 images to be resolved, is also this is theta. Theta is nothing but this b is this distance into theta, which is this distance is v into the previous value, which is here. So we can write sine beta is nearly same as tan beta is equal to if we take this is our angle beta. This angle beta is what? Tan of this will be a by 2, half of this divided by this distance. This distance is nothing but focal length of the lens. Magnification is defined as size of image over focal length. Why it is V by F? What is V? V is this distance and F is this distance. This is same as ratio of this distance divided by this distance. Ratio of this distance to this is same as this distance divided by this distance. That is why it is magnification. If we use this relationship, our F is equal to this is one relationship and this is another relationship for magnification. So our magnification becomes V divided by this value this is same as we have defined our B, size of the image over distance or size of the object, which is we can cancel from here. We get cancelled from here. What we left is or dm, the minimum distance that can be resolved is this is when the media is air. For air, we know that mu is 1. But in case this media is not air, then we have to correct this formula for mu, and which is this is the refractive index of media. And this term is also known as numerical aperture. This was for microscope. In case of telescopes, the minimum angle that can be resolved is given as where D is the aperture or dia of objective lens. And resolving power 1 over d theta, the minimum distance that you can resolve becomes d by theta. D is the aperture of the objective. This is the formula for telescopes. Next topic is we discuss eye defects. I'm sure sometime or the other you must have used glasses for reading or for seeing distant objects. If you have not been using it, you're too lucky. Let's see what can be the defects. One is that you are a nearsighted person. This is also called myopia. In this case, you can clearly see distance objects which are close to you, but you cannot see the objects which are far away. So there's a term called near point. Near point and this is a distance from, both are distance from eye. And what is this distance near point? Person cannot see object closer than near point. He can see far point. Let us say this is our eye. This is our near point. He cannot see anything which is more closer to this, but there is no restriction on seeing objects which are further away from the eye. Okay. Far point is what? It's just the opposite. You have an eye. You cannot see. Far point is the farthest point that you can see. Yeah. And if you bring anything closer than that, you cannot see it. If, for example, this distance is 4 point, then the person can see anything placed closer than this. But if he goes away from this place, he cannot see it. This is the farthest point from the eye which he can resolve, which he can see. Now, this is a condition for no, sorry. If a person is nearsighted, this is a condition for myopia. He is able to see closer objects. Okay, but far objects he cannot see. Similarly, people who are farsighted, this is hypermetropia. Far objects, they can easily see, no problem. Near objects, they cannot see. So these two conditions are opposite to each other. Now, how do we correct it? This is the case for myopia. The image is formed from distant object at this place, which is closer than retina. It doesn't fall on the retina. In order for the image to fall on retina, we introduce a concave lens. What it does is, a concave lens makes the image coming from distant places coincide with this far point. So when this happens, the image is formed, seems to have formed here, and his vision is corrected. So for myopic patients, you have to use a concave lens for correcting their vision, so that the distant objects focus at his far point. And if we call this as X, then the power of the lens used is equal to 1 over focal length in meters is equal to minus, because this lens's focal length is negative. Now let's take another case, second case. So for far-sighted person, what happens is that if you bring the object closer, then the image is not made at the at the retina, it is made beyond the retina. Now, how it can be corrected? It is corrected by putting a convex lens here. Now, by putting a convex lens, what happens is the objects which are clear, which are nearer, are made to appear to have come from this near point. So that's how you correct it. And near point is normally usually about taken to be 25 centimeters. So for a far-sighted person who is hypermetropic, you have to use a convex lens to correct it. Now, if we use a lens formula, if we take this distance of near point, which should have been 25 centimeter in the case of a hypermetric person, this is more than the usual near point. Let's say it is y. So what happens is V is formed, image is formed on the same side of the lens, so it becomes minus this is where the object is to be placed. If the object is to be placed here, we want the image to be formed at if the object is placed within this distance at this point, we want the image to be formed here. This is equal to 1 by f, or one by f is equal to or mind it, this is 25 centimeters. If you want to convert it to power, then you have to take all the distances in meters. So power will be equal to 1 by f is equal to, this was 25 centimeters, so this becomes 25.25 meters. And y also you have to take in meters. So this is the power of the lens which is required for a hypermetropic person.